It's a pleasure talking to you all. It feels nice to be back to the alma mater. Nice to address some of the IISc's brightest students in this room. So today I will take you on a journey. The next 45 minutes I'll at least take you on a journey of what is a SERDES or what would be a wireline transceiver. So we will talk about some portions of the transmitter, we will talk about some portions of the receiver, and we will see what are the challenges when it comes when you need to hit a data rate of 20 gigatransfers per second. Right? Quick works. Along with, so the photographs that you see here is kind of testament for what are the activities that you could carry out at IISc. So not just being an academician, you will also get to be a researcher, you get to be a leader by participating in events. So you would see the leadership of the wonderful students before me. And this is an opportunity that IEEE provides. Along with that, we get to interact, all of outreach activities that we have seen. So we get to visit schools and colleges, meet these people, share our knowledge, and try and inspire a few people to come into this tech area and, if possible, join IISc as a future student or a graduate student. During my free time, what I've realized during COVID was kind of getting bored not visiting office. So I had a little extra time at hand. So I started off 2 YouTube channels, one of which is exclusively on VLSI education, where we try and reach out and try and target people who need education, who need support in the VLSI side. Though there are a lot of other websites, this is another initiative we thought to do it. So I started off with that. One thing what I did was all my lectures, which I deliver at various colleges, I teach at 2 universities. So those 2 university lectures are hosted on the YouTube channel, and they are free for all the students to watch, and everybody can leverage that. Like Soham mentioned, while doing the same, I also started teaching on Udemy, and where I offer about 8 courses right now, mostly with regards to being in the VLSI domain and having an understanding of what needs to be done, starting right from the basics. We try and cover topics on high-speed serial links, LDO, PLL design, VCO design, and capacitive sensing, what we do, which was good part of my PhD work. So a quick brief about the projects which I got to carry out in the last decade and a half. So the first one is principally my PhD work, basically working on a lab on a chip, which is instrumentation big grade capacitance measurement, where you try to reach femtofarad of capacitance measurements that you could do. While working on this, also came across BIST, built-in self-test, and built-in self-test led me to do something called an electrothermal test, meaning how can you test the parameters of any functional system by measuring what is the heat dissipated in the system. So trying to use thermal equilibrium or laws of thermal conservation, where amount of heat dissipated is equal to 1 minus your performance knowledge. So that is an indirect way of measuring the system performance. This became a work which I was closely related from after my PhD, where it led to high-speed SERDES design, designing systems from 1.25 gigahertz all the way up to 40, 20, 32, 40 Gbps. Most of it was for serial I/O, targeting protocols like PCI Gen 4, USB 3.2, MIPI, M5, C5, and D5. So various 5 analog portions that you could design, mostly on the wireline transceiver side. So you will be seeing a lot of the content from this particular work. While we're doing SERDES, you also understand that clocking is an important phase. You need to build PLLs or various other clocking sources. So understanding how to get LC and ring oscillator based PLLs, low jitter, high performance, various other combinations we were able to do. Along with that, I tried to work on some hobby projects, basically on energy harvesting, where you had understanding what do you do with energy harvesting, how do you do with backscatter based communication, try and understand extremely low power communication or IoT projects and how you could implement them. While doing that, power to power converters where you do LDO and DC-DC converters also came into the picture. So one final thing that when you are experimenting in your research work and you meet a lot of people, if at IISc at least, you get to meet tons of researchers. Frankly, in this campus, you have about 2,500 researchers every year. So your interaction is always with them. And one of your lunch table conversations move, say, we have drones in the lab, aerospace department. We have IoT in one department. We have sensors in another department. But how can we use all of these to work on agriculture? Can we see what post-agriculture what happens, or during beginning of agriculture process what happens? Farming, surveys, understanding various reforms, what we can try, technological contributions that you could do. So these lunch table conversations became a project, started working on them, did a few interesting things, and went into drone survey-based analysis as a hobby project. It continued. So this is the wide aspect that you see, and I will now try and give you a brief overview about why do we need high-speed serial links in most conditions. Some might be new, some might be old. This is a radar-based system where you have a vehicle moving in. But once the sensor comes in, how is the communication happening from the sensing various points to central node? We need high-speed serial link for low latency work. So low latency, higher throughput, better computing power, you get the right input there. So you need serial links there also. Next is chip-to-chip communication. So a typical example would be your handsets, mobile phones. So your handset has a CPU, a GPU, memory, various sensors, audio and video. So all of these can be, they need communication to each other. So you find a lot of chip-to-chip communication. Typical works would be the MIPI interface, where you have M5 for the memory interface, C5 for camera, D5 for display, and various other works. Chip-to-chip, data and control, multimedia is all over here. And the next comes is when you're working with a mobile front haul or back haul. So what does this mean? You have your servers and you have your optical interconnects that are there. And this, when you need to talk to each other, you typically use an optical communication, right? Optics carries the information. But before optics, what was that? That copper. So most of this communication happened through copper, and it was all serial lines. So there also is very much interesting. If you look at some of the other activities, if you look at the center of this figure, you will see this is the 10G, 25G, 100G. What does this stand for? This is basically your Ethernet protocols, which happen with high speed data connectivity happens within your data centers or your end centers or your server network and all of that. This is called forms of closed loop work. For each of these units, you will find Ethernet being a major connectivity right now. Before, now it is all going to be optical connectivity, where you're trying to get a much more larger bandwidth to work with. Similarly, when you need to perform the backbone of your cloud activity, so all your activity is on the cloud, it is essentially still a machine sitting remotely in some place. So this machine also needs to communicate with data. There also you will have high-speed serial links offering the wide bandwidth of work. So in essence, what I want to say is data is going to be the currency of the world, future. So how you play with data. So data transport is again activity. Data storage is activity. Lowest speed, highest bandwidth, highest speed, highest bandwidth communication is again possible with data. So wherever you go, you will see jobs for this activity. And all the engineers will have a lot of challenges, and we'll try and discuss a few challenges going forward. So we just have covered the motivation. Now I will tell you, take you over a short journey on interconnects, what can happen, and how newer interconnects, as we go for higher data rates, what are the challenges come up along with that? How do you solve them? And then by meaning of solving them, you see what are the kind of jobs that you will see in the market. I'll speed up here a little. So everybody is aware of chip-to-chip communication, but the medium that happens are multiples. You have copper is principally the medium over which the information travel happens, which could be your PCB. It could be on the die also. So die would be aluminum or gold, depending upon what is the material that is being used there. So we see multiple things working. I'm not sure. So if you look at the older, when you're looking at 10 Mbps kind of a range, say almost 50 years back, you would have a lumped capacitance being modeled as your channel. That would be the closest approximation, and you would work very slow. So what would be your effect that you check? That would be your RC, rise time, fall time constants, predominantly will be there. Next, as your speed you wanted to increase, you found how do I compensate the capacitive loss. So you came up with adding some inductance to see can you compensate some of them. So then became your transmission lines. But this was not sufficient. Transmission lines further had a doubt that what would be, how much of the loss can you further reduce? So they again went to compensate. How do you do point-to-point systems at very high speeds? So decision was taken, instead of doing very large distances, we will do shorter distances, but have multiple repeaters so that we can convey it over a longer distance. Finally, it came that extremely small current where you're hitting, where you're greater than 10 Gbps, 100 Gbps in many cases. You find that your channel has a very nice model. Channel is being modeled, and the loss due to what happens to the data due to the loss here, can it get compensated both on the transmitter side and on the receive side? What all can be done and then taken from there. So these are the various methods a channel loss was modeled. Going into a little deeper to understand what actually happens is, if you transmit the data with this bigger signal, as your frequency gets higher, the amount of loss that your channel sees becomes lower. So you will see profile of the signal amplitude coming down, the amount of strength present coming down. That is attributed to what is the loss present in your channel. This is particularly showing for optical channel where you see at maximum about 2.5 dB of loss per inch or for longer. But in some cases, for example, in PCI Express, you would see the losses being to the tune of over 30 dB or 2-inch or 4-inch loss. So how do you compensate 40 dB of loss is what was taken forward as understanding what we do in the design work. Along with this, two other things came into the picture to understand the loss. One was DC coupling and AC coupling. Could you please tell me what is DC coupling or AC coupling? Or DC coupled system or AC coupled system?
So in the AC coupled signal, you don't allow the DC biasing condition from this TX block to pass onto the RX block, or else it will just disturb the DC biasing point of the transistor present in the receiver. So in the AC coupled, you just remove that DC operating point, and in the DC coupled, in that DC bias along with the AC signal goes directly to the receiver, and that bias point itself biases the transistor present in the receiver.
That is correct. So exactly what you said is AC coupled. Here you see DC gets blocked with the AC part, whereas in other things you will just follow through. Now there are two things happens when you have AC coupled, right? You need to have it to reduce the amount of reflections. You need to terminate some of them. So you have either supply based termination, or you have DSS based termination, or you have a common mode or any predefined voltage based termination, and to ensure that your reflection is much lesser and your data transmission happens better from the channel to the receiver. Otherwise, the data at the receiver input can get reflected back and cause an issue in the channel. So this is what we will do with coupling them. So quick overview. So we just understood that serial links, why did it correct? Okay, high-speed communication is needed. But why serial links? People started off with the concept that we will have one lane for one data transmission. And they said, what is the easiest way to increase the bandwidth? Add multiple lanes, and that started with your parallel bus or your parallel links. But as the data rate started increasing, having so many parallel lanes together became an issue because each was cost. And when you're designing very high systems, if you have so many parallel links, you end up paying more for it. So at one point of time, decisions were taken in the technological world which say we will move back and make all this parallel into serial and make the serial line extremely fast. Does that only at the receiving end, at the transmitting end and the receiving end, you will then break it down into multiple smaller speeds but wider bandwidth and take the data inside. So it's an example that you have a parallel in serial out and a serial in parallel out. So you maintain the same data rate. For example, you have an 8-bit data at 125 megahertz. You take all of the 8 bits at 125 megahertz. If you multiply them, then you get 1 bit out at 1000 megahertz or a gigahertz. So you ensure that the product is the same, the throughput is the same, but it is easier to handle multiple parallel lanes or a serial line. So it is better to handle multiple slow speed parallel lines, and high speed single lines is easier to handle because the number of channels would be lesser. So that is what the essentially idea came in, because along with the cost of it, how is the cost defined here? Along with the channels, you would need package, right? Each of these needs to be packaged, and for each of the package, a pin needs to be present for the data transfer. Now, as the number of pins increase, the cost of the package, the size of the package also goes up, and the reliability along with that also enhances. We need to enhance the reliability, or it is already less reliable. So with that, they said, okay, let us trade off speed and cost and get serial links here. So all the parallel interfaces which are less than 100 megahertz or less than 200 megahertz now became a multi-gigabit serial link. So the way you go is you will get your transmit information from the serializer following the blue line. This serial would have a multi-bit serial link, single pin at multi-bits, multi-gigabit go into the serial deserializer, and this deserializer would convert the serial into parallel and get this parallel into ASIC information. So this ASIC, what we is notified here, is going to be your digital domain or your RTL blocks, which are more parallel based oriented. So it will be low speed parallel becomes high speed serial. So that is how it comes across. So that is how the name came, SERDES, which were the first 3 letters of serializer and deserializer put together. And this made cost mitigation easy for quite some time. Now let us go into what are the challenges typically that you face. The first challenge that you face is as your speed increases, your time constant, the time or pulse of each data is reduced, and whatever existing R and C are there, as the frequency increases, they start degrading. So when you have an ideal data, this would be a rise time, but as your frequency increases or there is a small change in the minor frequencies, the I would reduce because the jitter would be more. You will see more number of rising coefficients there. So you would see the clock which is coming here. If it is not clean, you would also see a jitter impact over here, or your eye would shrink because of the amount of noise that is present. So this became one of the challenges, and it also became a testing methodology to say if my eye opening is good, my link connectivity is good. My eye opening is bad, my link connectivity is bad. Meaning there is a limitation on the maximum frequency at which we can go. So how do we find out what is the most optimal one? So for each data rate, an eye opening box was defined. So if this box was clearly visible, which is basically a virtual visual understanding, it is said that it is a good for that particular data rate. So as sometimes what happens, as your data rate goes up, this box height also reduces, width also reduces. So you would use this as a measure or a quality measure of how the link is. Now further what happens is you have to understand that when you're transmitting data, you are transmitting it in the time domain. But most of the analysis is done in the frequency domain because it is easy to analyze in the frequency domain. So what happens as your pulse starts becoming smaller for each of the work, the pulse as it progresses through the channel, it starts spreading. So what does this mean? Once it starts, essentially this is the area under the curve, right? The energy that is under this is put into the channel. By the time it comes out, the energy under this channel gets spread out. So this is called pulse spreading. So what happens with this pulse spreading? This is the width of this pulse now gets overlapped with its neighboring or adjacent symbols. So this is called interference, or it is called inter-symbol interference. So what does that mean is, significant portion of the next pulse is taken up by the previous pulse. So now you do not know the contribution that you see finally in the pulse is only because of it, or is it because of the previous pulses and the future pulses that will come into it. So this is understanding you have to understand about pulse spreading. Pulse spreading further happens when you have a lot more attenuation. So how do you understand attenuation very easily? With the frequency domain. You typically maintain your operation up to -3 dB, where you say you can handle up to some amount of loss, beyond which you do not use it as an active space. So as the frequency response that is shown here, you will do a frequency response check. As the frequency increases, what is the total amount of gain in your system? Or conversely, how much loss is the system seeing from DC? So once you see the gain rolling off, and by chance that your operational frequency is in the much lower domain, then you need to compensate that by doing some circuit technique to ensure that this is compensated and you ensure getting a flat response overall when you take it from your input to the output. So that basically is called link equalization. You try and equalize that link. Okay, so the bandwidth limitations is compensated with those circuit techniques. So now when you go into equalization, what does it happen? So we will work on, this is the problem statement. We have a pulse, the pulse is spreading. Now what can I do to ensure that this pulse is not spreading? So the way we did this, or why method was followed was, ensure that this total pulse can be corrected at two places. One, you can either correct it at the receiver side, or you can correct it at the transmitter side. So there are both methods are used depending upon what is the data rate. As we are hitting greater than the 10 Gbps speeds, both these techniques are needed. You need to correct it both at the transmit side as well as on the receive side. What happens in the transmit side? You do something called a pre-emphasis. What does that mean? The pulse which are having a smaller time, you try and emphasize them much more. Okay, pulse which are wider in nature, you reduce their emphasis. So this pulse, the total energy of this pulse is now transferred into two systems. One pulse where you are reducing it before, which is typically called pre, and another energy pulse you are doing it as a post. So what does this mean? This energy which is there on the left hand side, this curve area, for people who are seeing on the bridge, I'm not sure. For people, okay. So on the left hand graph, in this space between the green, red and the blue, so whatever energy is used here, this energy is now reduced in the pulse beforehand itself, such that this line falls aligned with the red line here. So whatever energy is there is reduced, and after this energy is reduced, you will see this width as on the top, it is very narrow on the top of the pulse, that gets widened and brought down, height would reduce, and then you would equalize this post. So this is called pre-equalization, which typically happens on the transmit side. This is post-equalization, which typically happens on the receive side. So taking in both the considerations, these changes in the signaling method is introduced. So this here now your signaling changes. We'll shortly describe how that looks for you. The signaling changes and you do. The next challenge that we typically encounter is noise. When I joined for my master's here at IISc, my advisor told me, be thankful for noise. You know why? Noise is the only reason you have jobs. If there was no noise, this circuit technique is from the 80s. Nothing has changed. Essentially, nothing has changed. It is only the presence of these noise and you trying to achieve a higher performance. You have jobs for yourself. So respect the noise, because if you don't have noise, you will go away. So sometimes when there is noise in your system, be thankful that you have something to work on. Okay. and that is also a metric of how much of noise can be removed or can stay back. So if you look at the noise, you have power supply noise. So every power supply will have noise. So every precision system will have an issue. Every non-precision system will have an issue. Linear circuits and non-linear circuits have an issue because everything is applied. So that is one constant problem you need to solve. Second is crosstalk. What is crosstalk? Like I just mentioned in the previous example, some energy from where it has to be the pulse goes into the neighboring pulse. So there is crosstalk. So this crosstalk needs to be reduced. For some places, it is called a near-end crosstalk. For some places, it's called a far-end crosstalk. What do they mean by near-end and far-end? From the transmitter to the input of the channel, and if you return back, you see a very small amount of crosstalk because there is no channel influence. But the moment you have the channel in its influence there, that is the far-end. As the signal goes far back, goes to the input of the receiver, and if you loop it back into the input, you will see it is much more degraded, or there is much more pulse spreading happening. So there is near end and far end crosstalk in all cases. So you will have to work with it. Another thing is high frequency coupling. High frequency coupling, it took me quite some time to understand what it is. But then I went back to the basic physics when we said that any current carrying conductor has a flux around it, right? Magnetic flux. Now every channel copper line is still a flux. Though it is on a PCB or on a channel, it is still the current carrying. And inherent essence of it is you will generate a flux. And when you put two lines next to each other, each one will interact with each other and cause noise. Right? Mutual inductance will generate, or a mutual voltage is generated on both sides. It is generally not beneficial. In some cases, it might be beneficial. That is why you have this decision problem of making ones and zeros, or a metastability state which comes in. This plays a significant role there in the decision making. Next is clock jitter. Clock jitter is, what is that? Unnecessary noise at the transition of the clock, either rising and falling, due to the environment in which it is present, or the power supply, or any other feature that is either due to the aggressor or some of the high frequency coupling or low frequency coupling getting into the picture. So this is one noise. This in distribution statistic nomination would be called statistical distribution, that you will see what is the probability of the symbol being true or false, and then make the false positive and true negatives. All these conditions will come in and you fill in the picture. Lastly, you will have device mismatches, which you will have to solve, which is localized to your activity. All these are the challenges that the engineering teams have to solve with every day or while they're doing design. I'll quickly go through three portions. I'll be a little fast here. Please let me know if I need to reduce the speed. First thing is a continuous time linear equalizer. This is the first block where the gain that you lose as the high frequency goes to the channel, that is tried to be compensated to ensure that you get a flat pass band of all frequency till your desired frequency is present. So what is the aim? This reduction in the loss needs to be compensated by this short peaking such that this line becomes flat till the region of request. So how do you do that? We have something called a continuous time linear equalizer. What does the name say? It is a linear what? So it is very similar, behaving like an amplifier till some extent where you have a gain. Beyond that, it is specifically giving a DC gain and a high frequency gain also. So how do you make one block work in two phases, both as an amplifier and as a high gain amplifier? So high frequency gain amplifier. So this is something that you do. But when you say high frequency, you should always picturize in your mind either an inductor or a capacitor is always in play. So you use one of these two components to ensure that where. But how and where you use it is where you will have to look into. So I will not go into the math. What I will simply do is to bring it here. If I remove these two components, it is essentially a amplifier. Okay. Now you are introducing an RC component which is frequency dependent. So you try and tune it somewhere. So you are trying to tune what is the maximum frequency at which you want to introduce this peak. So this is why it is called a peaking amplifier. You are trying to peak the gain at certain frequency such that your operational frequency bandwidth has got a higher frequency usage or higher gain usage. So I will leave this for future work. I just should try and be more visual. Now you may ask, what are the parameters? I have both R and C, which affects what? So this is a quick understanding. So if you have RC connectivity here, the resistance will try and reduce the gain, and the capacitance will try and move the peaking to the left hand side towards the origin. So this is the intuition behind what it is. So how does this happen? There is a pole and a zero in play. You will these two impact the pole and zeros. If you see the equations here, there is a zero here which is impacting RS and CS, which is the component there, and the same RS and CS also is affecting one of the poles. Hence, this combination you will use. One is the dominant pole which is present here, which is always never in play. So this is output driven. So your RD and CD is present here. You never get to play with this. The only play you will have is at the input side here. Only on the input side you get to play, nothing on the output side. So you can clearly see the input is on the source side. And if you look at it, this is called source degeneration if you have a common source amplifier. So you play with the source degeneration so that it impacts both the input, and this capacitor will kind of provide a short path at a higher frequency to give you this peak. So that is the physical aspect behind that. So now I did mention, right, that we do not have much play with RD and CD. We cannot do it. One way we can play is try and compensate the effect of the capacitance using inductors, so that you can get a much wider bandwidth. The pole can be tried to shift out a little so that you can get a little wide bandwidth. So that is one work that you do. It's called inductive peaking. And the problem with inductive peaking is inductors at this frequency is pretty large in size. You do not want to lose so much area. So you try and implement that by using an active inductor, which is a combination of transistors and capacitor only. You will not have an inductor which is larger in size. You will save space. So this is one of the tricks that works, which our team introduced to ensure how we can do the active inductor. So introduce a transistor along with a resistor here. This is your typical active inductance where you try and play with the output impedance of your system, which is tuned to a particular frequency. You try and get that and get a various work. So this is a quick show about the. So if you look at this is the schematic where you have a differential pair. The output impedance is only played with, and these are the two other. These are the two other blocks where you can try and reduce the impedance at the output. So it's trying to introduce a negative impedance, try and remove some of the impedance by phasing it out. So this is a layout for that particular work, and effectively what we tried to do was this particular CTLE, from having the channel response as this, you are able to recover up to 18 dB at 10 gigahertz. So you try to achieve this flat band all the way here, and then this will give us sudden drop. So till your region of operation you can do. So in case if your system is operating anywhere between 1 and 10 gigahertz and is seeing significant loss, that gets compensated with this flat band. So for example, if you're working at say 2 gigahertz, 1 is here, 2 is here, you're still in a flat band. This very small amount of compensation does not have much value. Same thing you do it at 5, 2, 3, 4, 5. 5 will actually see at least half of it. So 9 to 10 dB can be easily recovered with this. 10, you're able to straight away get a 10 dB recovery. So this is what you call equalization of the channel. So this is on the receiver side. So this is a quick example to show how when you tune the RS and R knobs, how the gain gets spread. So the DC gain can go from 0, from a negative value all the way up to 2 dB, and your peak you can vary across depending upon where you want to tune it. So this is very layout sensitive. So you have to ensure that all this tuning can be done after the layout is done with a careful understanding of the system. So quick to show, okay, you have shown me mathematically, so show it to me physically. How do you validate that? Easiest way of seeing this. This is a signal transmitted with the various pre-emphasis that is present in your transmitter. And here is a very small I. literally no I present in your receiver that we received. So how do you recover this data? With the CTLE, you are able to recover by increasing the I. Note the value that we get. Here it is only 10 millivolt, so this is probably about 2 to 3 millivolts. This 2 to 3 millivolts being able to recover, you are looking at 508 to 530, around 20 millivolt is what you get, the 16. Up to 16 millivolt is what you can bring it up. So 8 times you have been able to increase the gain. Now I did mention, right, there is a metric. Your eye diagram will tell you how good your eye is. So this is what the eye looks when you, the left hand side figure is what the eye looks when you receive it before the CTL. After the equalization, you get a clear eye opening. From no eye opening to eye opening, this allows you to understand, can you take a decision based on this. Now if you put a decision or an inverter here, if you put sufficient threshold, if you go over the threshold, you will be able to decide that anything above this line is a logical 1. Anything below this 0 is a logical 0. So you can decide.
Is the equalizer an analog circuit?
Equalizer is an analog circuit. This is the equalizer. This is the equalizer. It's an analog circuit. Okay. So if you are looking at, okay, if you are you referring to the digital communication one? So there are some equalizers which are present, but those are at lower frequencies. So at lower frequencies, you can still build it. Effectively, it would be like an FIR filter kind of a thing. So you build a digital DSP-based FIR filter for equalization. It happens at lower frequencies. Yeah. Higher frequencies, you prefer analog because you do not have digital still running that fast. Right?
Get the block for the switch capacitance, because that would also require a second clock source which is very near the transmission frequency.
That is correct. Switching does. Oh, good question. So now, for example, this is a switch which is present here, right? I do not need to turn on this switch at this speed. It is only to tune this way. So it is a low frequency. This is again a low frequency switch to only choose which one do I want. So it is not in the signal part, it is not the high frequency signal switch that I need here. In this particular implementation, you would do that. If you really need to do a switch capacitor, then you're limited by what is the turn on, turn off time of the switch that you use, and that is the maximum frequency that you can work.
So one more thing, you recovered some of the loss using that
Yes.
CTLE. So how much power was burned in this circuit?
Quite a lot of power gets burnt here. So it is again a trade-off. Typically, we are looking at sub-milliwatt applications are also there. More than tens of milliwatt applications also there, subject to what is the maximum frequency that you are trying to do. So it is always frequency dependent, because as the frequency goes up, there is a non-linear relation with the power, right? It is the hyperbola kind of performance is what you see. So you'll actually see much more power for much higher frequencies. So yes, power burn will be there, but you need that to recover the signal. So it's a trade-off. Performance trade-off that will be.
The power depends on how closer you want to get.
That is true. How, if you want to get ideal one, you try and burn as much power you will get. But beyond one stage, you will not see the benefit. So you only hit the sweet spot. You can go actually further optimize it, but you do not get a much benefit out of it. So you stop at a place where it's a nice sweet spot and you can work it. So this is CTLE, which is on the receiver side. Now I'll briefly go up on the feed forward side, meaning how can you predictively send the data before itself such that less compensation is needed on the CTLE. Right? So this is what happens. Same thing here. You will do this is no equalization. Right? The red line is the regular pulse that you have sent. Here in the TX side, you need feed forward. So you try and introduce some tap. What are those taps? The tap I bring you back here. So this is your signal after the small pulse is transmitted to the channel and received here. So each of these pulse, now you break it down into one time unit that you have here. You break down this entire thing into time units and see how many time units is your signal spreading to. This particular signal, it is starting from -3 going up to 10, meaning 13 unit intervals it is traversing, meaning this pulse can impact 13 pulses or 13 data points. 3, it would be before, which is on the rising time, rise time curve. or rising edge, and the falling edge is on a much higher number. So each of these pulses you try and find out what is the energy, and then say this is the amount of energy at each one of the pulse. So this energy number normalized to the regular value becomes your coefficient. Okay, what is the coefficient of the tap that you are going to use? So here you will see all these are positive, more than 0. But when you start equalizing, to ensure that all this energy gets fit into this, you have to go sometimes negative, smaller, up and down you will go. So there it comes your negative coefficient. So the negative coefficients come basically here. So to recreate this action, right? This is the expected action that we have. You will recreate this blue curve with a 3-tap coefficient. What are the taps? One is at the tap which is at the center. 1 unit to the left is 1 tap. 1 unit to the right is 1 tap. So 3 taps you will take. And you will recreate this blue graph in the TX side. And that will typically look like this. So this energy distribution, if you see here, the bigger one is on the left-hand side. That will come here. The smaller one on the right-hand side will come before. So the energy is getting distributed with these 3 taps. So you see 1, 2, 3 units. Then 3 units you bring there. So this is called your equalization, where you send the data beforehand itself. That's why you call feed forward the data. So this is called feed forward equalization. So how do we do? This is your typical digital one. You said digital equalization. What you will do? 1 unit of delay. So you have a delay element. Another unit of delay, you have a delay element. So 1 coefficient is your center, 1 before, 1 after. If you get these 3 coefficients, this effectively becomes a final output that needs to be transmitted to the channel. Now, many standards have been developed and you have come across this kind of a pre-emphasis filter. So what does this pre-emphasis mean? These are the various voltages that you see, and for these voltages and this frequency of the signal, you will change the height. For example, VA here is the maximum voltage that you get for highest changing data, meaning you have a continuous toggle of 1010 on your data, which is the highest speed, so you have maximum height. But if you have a series of ones or a series of zeros, that means there is no change required. So this phase would probably introduce that particular change, meaning you have a series of zeros or ones. This is typically a series of ones, so you try and reduce. So as a series of 1, what happens? This frequency reduces, right? So you're on the right hand side toward the origin. Your frequency is lower. You have better gain in your system. Following it? So this is your loss, right? The highest frequency would need the highest amplitude. So you keep it here. As the frequency, or if you send a series of ones, what does that mean? Send a series of ones is a low frequency signal. So that signal essentially comes here. So it doesn't need significant gain or doesn't undergo loss. So that is why you send. Now this small change here is a 0 to 1 or a 1 to 0 transition. So when you need a transition, you need a slightly more gain. And again, this will be a 1 to 0 transition, highest frequency to back. So that's why you will have VA and VD almost being same. Okay. So what they did was, this is called a de-emphasis. So you de-emphasize VB with respect to VA, meaning this frequency reference. Then you do a pre-shoot, meaning you need to shoot up the value a little. So that is with respect to C and V, meaning when you have a 0 to 1 transition after a long series of ones. Finally, you have a boost again, meaning after series you send, you get a very short 0 to 1 signal there. You again have to boost up the signal here. You get a VD by VB. If you see, for these two, EC and VD, VB is your reference, but for VB, VA is your reference. So this is the voltage. So this is the typical signal that gets transmitted from the TX into the channel. So that is what we do. And here, this is a quick understanding. Now, how do you do pre-emphasis there? You typically use current-based control. So you increase the current, decrease the current to increase or reduce the amplitude. Basically, V into IR. I is more, you get more amplitude. I is less, you get less amplitude. Use that concept and get it done. So it's a very simple one. You have a driver and you monitor that outputs. As you monitor the outputs, you also get a delay element, send it to a pre-emphasis driver, attach it back and use it. So you get 2-3 signals delayed overlapped here. So this is going to be your actual signal, but this would be the emphasized and de-emphasized signal which finally would go out. So this is your input of the transmitter. This will be your output of the transmitter. Okay. So this takes care of the precursor portion. The noise amplification, you will have to correct it in the receiver side. So a quick example of how this would be implemented. So X, this is again your FIR filter. So this you can implement. You can implement easily on a digital platform and get it done pre-emphasis. So this is what would happen. If your channel is like this, you de-emphasize the low frequency channel and re-emphasize the high frequency channel. Ensure that you have a flat line till the frequency of your interest. Okay, so now we have understood what happens at the pre-emphasis side. Now we will go to the post. Post is now on the receiver side. So this particular decision feedback equalization happens after the CTLE is done. The CTLE is already amplified certain value. You get a certain amplified. So 2 millivolt became 20 millivolt. Now 20 millivolt needs to become 800 millivolt swing. How do you do that? How that the gain factor comes in? We will again come with that here. So we have addressed these tabs, pre. Now you try and address these post. So this is your signal which is after the channel. Now to equalize this channel, you have to reduce this energy. So you try and reduce it here, pull this energy completely down, such that this energy is locked into the negative portion here. This energy again you pull it down back. Now this flat line will start staying down. Do we need to go this detail? Again, it's an implementation factor that you can play. So you take two tabs. So you take two feedbacks from the data. So that is how it comes as a feedback channel. So after you take a feedback, you sum it up. After you sum up, then you take a decision based on that summed output. Is it a 1 or a 0? So this is where it is decision, feedback, equalization. So that's where it calls as DFE. So you do it at the receiver. What it tries to do is, the main aim here is the inter-symbol inference. Interference needs to be reduced. So this is again what it typically looks like if you have no CTLE, no amplifier before. Straight away you have this data which is coming, and then we apply DFE, and I opens up for you. Okay. So based upon this, again a decision feedback is taken. Now, how do you get this data? Again, if you look, this is your CTLE, looks very similar way, RD and CT. Peaking amplifier is present. Now, at the output of this peaking amplifier, you need to add tap coefficients. Now, what is this tap weight? Current again. How much current you add or remove. So you add that current coefficients and put it as a PG. So your data P, data N, data N, data N. So how much of information is coming? You can choose that many number of taps. Each one will have a different tap coefficient, and you add the final one and then take it to a sampler to sample the data. So that is what is happening here. So your DFT is done. Not all coefficients that you need is taken, and then you sum it up and finally latch. So this is your slicer or your comparator that you can use, or your data. So what are the kind of summer that we use here? Again, when you say current mode, so you need to sum with the currents itself. So current mode is easy to sum. You bring any number of current channels to a particular point node, current will get automatically summed there or directed, depending upon where you either have a low resistance or high resistance. Accordingly, it fits up there. So that is how it is called current summing. So this is a complete effect of what you would do at a CTLE and a DFE. So this is your CTLE portion here. This is your DFE portion. This summer is your current mode summer. So 1, 2, 3 inputs, 1, 2, 3 inputs and a single output. All are current mode inputs. So this knowledge is brought from your traditional bipolar transistor level. Right? They are all current mode activity. So this is also current mode activity indicated. So this is how you get the complete DFE architecture. So now what happens is, whatever the noise is there doesn't get amplified. Only post-cursor cancellation only happens. So that is why you need to use both CTLE, DFE, and FFE to get pre and post-cursor coefficients. Now the question is, now how do you determine what are the coefficients now? So quickly we will go. So this is the number of segments that you divide your I high with. So if your eye height is on the maximum side, you take a positive value. Maximum, little lesser, you need to make a negative value. Likewise, the flip of this one over here. What is the math or logic behind it? Again, with the same model that you use. You'll have two samplers, one for the X sampling, one for the Y sampling.
In the previous slide, why was the CTLE on the receiver side?
CTLE is always on the receiver side. FFE. Feed forward equalization on the TX. So it is TX FFE, RX CTLE, RX DFE. Remember, you will not forget. Okay. I will not go into this. So this is basically says what should be your positive and negative coefficients. How do you determine that? And based on this, a lot of people have now done adaptive solutions on this, creating a feedback loop and creative adaptive solutions to change on its own, independent of what is the data rate that is coming in. So you don't have to manually do it. The system automatically takes feedback and does it. So a lot of solutions are there on adaptive work. So now I'll quickly last 3 slides, just a quick memory refresh what has happened. See, you have in this overall link that we have built, this is on the transmit side, FFE, transmit, channel, CTLE, and the DFE. In the DFE, one part I have not covered is going to be a CDR, which is a clock and data recovery, because for time constraints I did not introduce that. That is to do. So here what you do is you understand what are the kind of terminations happen. Okay, AC coupled, DC coupled, and various terminations. Second, LVDS, meaning low voltage swing can have. When you do not have a low voltage swing, you can do a high voltage swing. Then you do a channel equalization on the TX side and on the RX side. And finally, coefficients adapting. How do you adapt the coefficients for each one of these taps that they say, and then bring it up. So these are the various problems you will typically solve. And now for the same architecture, there are various variants as you go for higher speeds. Note, this is only non-return to zero signaling or NRZ signaling. Another called PAM signaling, which we have started using for beyond 50 Gbps. So 56, 112, 224, 488, 448, multiples of that, you would see PAM4 coming into the picture. So what are the takeaways that I want you to have from this work is high-speed serialings are needed. You will see a lot more of them being used no matter what. Achieving high data rates on a copper is tough. That is why now they have essentially gone into optical, and which I think Janvi will cover quite a lot in detail if given the chance. Now we have to save silicon, we have introduced active inductors. Okay, serialings can be great for cost saving and also package BOM cost or reliability cost saving. And one more thing is there are lots of jobs in high-speed serialings. So after your master's or a PhD, if you're working, please look into this while you do your industry internship, or at least refer one of them when you do that. So quick acknowledgements from all these faculty members for them and the various people presentations I've used. Thank you very much. You've been a great audience, silent albeit, but still very great. So thank you. I'll take questions. Any questions on the bridge? You can unmute and speak. Yes.
Regarding the UCI specifications,
Come again?
the UCI, it is basically just PCI.
UCI is a combination, right? So it is taking the best of all that is present and it's combined. UCI is universal, PCI is peripheral. So PCI is typically used only at the peripheries and what. Here, this is a proposal that you can use it for everything. Short range, long range, all kinds of peripheries. Essentially, if I have to explain that in the simplest way, that would be it.
You will also need to incorporate the adaptive signal. Because you have a silicon interpose.
Correct.
But still, you can't say what other systems you are running.
Okay, now here's a simple way of explaining the context to this talk. Silicon interposer is a channel, right? you are connecting various other devices to the channel. Now, each device has its own frequency of operation. So it is designed for a certain frequency of operation. So though you have multiple bits, each bit has its own frequency of operation, each data rate at which operates. Each one of them is adaptively equalized and kept. So the protocol allows all of these, but you choose which one you want and keep it there. Yes, you can add adaptivity to it. Coefficients you can change over a period of time. Is it mandatory? No. Is it a good feature to have? Yes. Is it cost saving? I don't know. It's again a trade-off, engineering trade-off. Hope I answered your question.
So what is the typical length of this SERDES link that you have?
Okay, typical SERDES link would be, say, PCI, we have heard of, say, 4 to 12 inches, okay, because that's on a motherboard. Okay, DDR would be about 6 inches. Okay, that is where your pin would be. If you open up one of your DDR cards, what is the amount of link that you would travel? About maximum 6 inches, typically 3 to 4 inches. Now, if you are putting a cable, if you're connecting two systems via a long cable, now you are limited by the signal integrity of that cable. So you'll have to put a retimer or a buffer or a repeater to at equal place where you are seeing losses. There again, it depends what is the frequency. If you are a low frequency, you have a longer cable. If you have a higher frequency, you have a shorter cable. That is why if you look at the micro USB cables are typically longer, but the Type-C cables are a little shorter. So that's basically said, higher the frequency, your repeatability has to increase. So you can keep shorter length communication on.
So one more analogy from the communication, digital communication point of view, since you know your pulse shape over here, so I didn't see any match filter kind of thing in the receiver. Then we use that to maximize our SNR at the receiver.
Correct. That is why we have, okay, now there are two things. What do you do in a match filter? Impedance match, right?
We pass it through a filter whose is completely what you can say, its impulse response is flipped and conjugate version of what we
correct. So what does it essentially do? So the filter is inverse. Okay, you have only compensation. But what does match filter actually do? Why you need matching? What is matched there? The impedance is matched. So if you have an impedance, same impedance, maximum power transfer will happen. It's a very old concept of maximum power transfer, MPPT only. Just that if you have an impedance, for example, if you are, that is why sometimes you have a termination, or most instruments say you need to have a 50 ohm termination. Only then we will guarantee correct output. So 50 ohm and 35 ohm, if you do, you will have a voltage reduction. Okay. So if you have a higher voltage, then what you see here will be a reduced voltage than what you see here. So for that, you try and match it. So that is why it's a match filter. Typically, match filter you will see when you're working with an antenna in the wireless systems. Wired systems, your CTLE effectively does the matching here because you're having a physical medium, you're terminating it, and you're continuing the medium inside. So there is no break as such. Whereas in an antenna, it is a wireless medium to a wired connectivity which the antenna enables. So you need some kind of a matching to understand that you get sufficient amount of signal from it. Okay. So the reason why I do is this is the main problem when you do all your RF energy harvesting and that. So when I dealt with multiple of my RF energy harvesting papers, first point is how much MPPT am I having, for what range or what impedance can I support well. If you have a wide impedance support, that will have good impedance. Like suppose 40 to 60 you can support, 60 ohms, you'll have it good.
And the CTLE that you showed, it's basically analog circuit, so it will be highly sensitive to the PVT variation. So if the surrounding temperature changes or something happens, then the functions that you showed, the peaking and all that will shift left, right, or upside down. So you compensate it for the PVT, do something.
We do compensate. Basically, that is where you bring in the concept of robust signal design, that you put in techniques such that even if the variation is there, you have sufficient methods to ensure that it is in the region of importance it is working. In the region where it is not working, it can go up and down. At least in that specific region, it's a flat band across PVT. I'm not saying that it will not be up and down. It will be. But in a region of interest, it is at least try to be as flat as possible. Good question, sir. Yes.
Okay, now we'll take a question from the online.
Yeah.
And then I will get back to the
If
in-person.
there's no
seminar.
online question, we'll go back to it.
Yeah. So Amba Prasad, now I'm going to allow your mic. So now you can speak and tell out your question.
That is one of the reasons why we are not amplifying the low frequency signal. That is a high frequency. So we will boost the high frequency. We are boosting the high frequency. Oh, for example, let me. What we will do is, tell me you're able to see the screen, right? So if this is how your channel roll off happening, what you will try and do is you will not put the gain here. This will be lower only. In this portion, you will try and give a gain. Okay. Finally, what will happen is this will essentially become a flat line. So this is the aim that we want to get. So this will be channel. This is circuit. I hope this analogy makes it simpler. Could you repeat yourself? Noise in which data? The incoming data. Yes, it will come. You have to work with it. That is why we have a second stage of DFE, where is it how much noise can we reduce, and so that you have a very clear distinction between the signal that is coming in. Yes. Could you speak up?
What would be the length or strength from the
Let's suppose how much recovery I can do. Suppose if I have a loss, there's a if I am on this side of the channel where I do not have much circuit to recover, then I say, okay, I will stop using it, stop using SERDES there. I'll go to a different medium. Typically go to optical medium and see, probably I'll introduce optical here itself. From here onwards, I can get a much more faithful response. Do we have some time?
We have time.
Yeah. Okay, it's a very simple answer. Let me work backwards with it. So the question is, what is the maximum frequency that we can achieve using a differential pair? So the question is like this. Now this is a 3 dB frequency, right? How much of gain is present? Now for this differential pair, what is the reason for this loss? Parasitic, right? Parasitics. So more cap is coming. Okay, more R is coming. As you increase the temperature, increase frequency. So at one point of time, your pulse stops looking like a pulse. Right? Your pulse stops looking like a pulse or performs like a pulse is your limiting feature. What is this? Basically a rise time, right? RC. Fall time and rise time and fall time. So depending on that, you will get. Another thing is how much noise can it sustain, tolerate. This edge will move left, right. This edge will also move left, right, along with going this. Now in this case, if this edge move left, right, the pulse is lost. So primarily, you will look at these two conditions to determine where is your maximum frequency that you can have. Single line.
Okay, so we have one question from Ashutosh K.
Okay.
From online. It says that is it possible to use ADC and DSE at above 1 Gbps data transfer?
Is it? Yes, you can use greater than 1 Gbps, but the question is your ADC going to work that fast? Make it work that fast. So that is why you have your, like how you have the RF direct connect receivers in the wireless domain, you can still have, instead of a sampler, which is a 1-bit sampler, You can put an ADC which is a multi-bit sampler. Now the question is, how many can you easily get the benefit of? Do it. Nothing stopping you. It's just again an engineering decision to say, is it easier to do using a simple amplifier or a inverter per se, as opposed to going to an ADC, which is like 2, 3, 4-bit ADC, because that is what is the speed that you can achieve or data rate that you can achieve at that speeds. So 4-bit at 1 Gbps takes time, right? It's far you are, because if you need 4 bits, look at understand how many sample levels that you need, voltage sampling levels. So that matters. Hope I answered that question.
Yeah. So if your question is not answered, then you can follow it up with any follow-up questions that you might have. Yeah. For the offline audience, any more questions?
Can we employ any kind of encoding schemes instead of boosting?
Encoding schemes will, okay. Encoding is a digital phenomenon, right? So what does a digital phenomenon do? Digital phenomenon increase the number of bits. Okay? It is time. That is the amplitude. Amplitude is not there. So amplitude is analog. Digital is only ones and zero only. It has to be clearly defined. You cannot play with the amplitude there. So that is why we need a boost in the amplitude time. That is why it's analog, may not be possible in digital. Yes, you can make it robust signaling by ensuring that it is well defined in your FFE coefficients, right? It comes under the well defined territory. Yes, that can be done. Pre-coding, encoding is done to ensure that the correct coding sequence will come or data transfers, right? Transitions. Number of 0 to 1 transitions is maintained uniformly so that you get it right.
Did package and wire bond cause any problem? Because you told that you had designed it for 10 GHz SERDES. So was it included as a part of the channel or?
Yes, packaging causes a lot of issue. So wire bond, again, the wire bond essentially behaves like an inductor at certain frequencies. So you need to operate your design below that frequency. If you are trying to operate at the inductor frequency, you have an inductor at the supply also, you have an inductor at the signal also, you have an inductor at the ground also. So if you really need to operate it higher, you should ensure that you incorporate these models into your system. So one of the reasons why wire bond went away and QFN came in or BGA came in was to ensure that this inductance value is lower. Flip chip came in for all that bonding. So packaging is essential when it comes to high-speed serializing.
Did this design require any kind of EM simulation and not like design the chip and package and then EM simulating it with some software?
It is always needed, but not in my purview. So some other team will probably do that, where they understand the package parasitics, understand how the package EM simulations are happening. Okay, where you do the finite element method based simulations, you do it. So tools are there, you understand what is happening, you design it, and then they will first take the package, design everything, and then tell the designer, these are your limitations of the package. Kindly include this in your design beforehand itself. It is not a later activity, it is a prior activity. Because it is too expensive to do it later. Because you'll have to relay out everything, start the cycle again. So rather than you do first the package, then begin with the second design. So there is a lead. There's an order in which package generally comes first.
I guess we should break for IT right now.
Yeah.
And further questions can be followed up towards the end, and we can also mail to Dr. Javed, I guess.
Yeah.